Okay, let's get going. So we're going to continue on talking about electric circuits. And so let's look at this one here. So this is again an old test question. I would say this is a hard one. To me, this is a hard one. Maybe not to you guys. And so we got this circuit here with a switch in it. What happens to the voltage across the resistor R4 when the switch is closed? So talk about this with your neighbors and see what you think. So what happens to the voltage across resistor R4 when the switch is closed?
Okay, so
Okay, so we've had about 2 minutes on this one, so let's go ahead and call time. And we'll look here, and so let's look at this. So we got a little bit of C's, a little bit of B's, a little bit of A's. Like I said, I think this is a hard one. So let's talk about this. Does anybody want to tell me what they were thinking? Be brave and tell me what they were thinking. Anybody? Yeah, up here. Okay, everybody, please, we're trying to listen here to one of our classmates. Okay, so the voltage across parallel resistors is the same, and so it should stay the same. Anybody else have something else that they were thinking? Yeah, what?
R3 and R4 are parallel resistors, so the current and then R1, the current that flows through R1 is equal to the current that flows through R3 and R4. And the larger, if R1, R3, and R4 are the same value, then like half of the current flows through R3 and half of the current flows through R4. And so the voltage is I can explain it with a voltage divider. So R1, R3, and R4 form a voltage divider. And when you add R2, it lowers the resistance of R3.
Okay.
Second resistance, so the voltage goes down.
So you think the voltage goes down. Okay, so that's a vote for going down. And what are we thinking over here?
The total resistance will decrease, so the current through R1 will increase. So R1 will take more voltage.
Okay, so a lot of good ideas. So first of all, so the thing from over here, the idea that the voltage across parallel resistors is the same is totally true. All right, that's always true, But the problem with that on this particular question is that we have this resistor here. If this resistor wasn't here, then these three guys would be sharing the voltage of the battery, and so their voltage would have to stay the same. But because there's this resistor here, all right, the voltage over here isn't guaranteed to stay the same. Now, in different cases, it might stay the same, but it's not guaranteed. All right, and so I think the explanations over here, which I'll try to paraphrase. All right, so what happens is here, so there's these two guys originally in parallel. You add another one in parallel, you're adding another route, okay, for everything to go through, for the current to go through. And so it's sort of counterintuitive, but by adding that extra one, you're lowering the resistance of your total circuit. And so what I'll sometimes do is just draw a little picture like this. So you've got this R1 here, and then you've got over here sort of just, I'll call this the equivalent of all those parallel resistors. So by adding a parallel resistor, that R equivalent decreases, okay? And so if I was to say, write out the total resistance of the circuit, right now I have two things that are in series. I have my R1 and this R equivalent. So by adding this extra one, the R equivalent goes down. This stays the same. That means the total R that the battery sees decreases. Okay, so just like he was saying over here, if the total resistance that the battery sees decreases, the battery is going to deliver more current. Okay, so by adding an extra resistor there, the battery is able to send out more current. And so how does this affect our problem? Well, we're getting a little bit ahead, but the thing that we're learning about today is that the voltage drops, okay, in a complete loop have to add up to 0. So let's just say we'll pick my favorite voltage, 12 volts for this battery. Okay, if I go around this loop here, and if I go this way, I sort of increase by 12 volts, which means when I decrease over R1 and decrease over R equivalent, those two decreases have to add up to 12, okay? And what happens is because the current coming out of the battery is more, all right, then that means the current that comes into R1 is more. And the voltage across R1 is just that current that comes into it times R1. So that stays the same. And so if this current increases, then the voltage drop increases as well. Okay, and so again, if we use this idea of a 12-volt battery, okay, maybe originally in R1 you came down 6 volts, and then when you go through the parallel of R3 and R4, you go down 6 volts as well. Well now, because the current increased, maybe that voltage across R1 is 7. Okay, and if it's 7, then that means I have to go down 5 through that other path to come back down to 0 again. Okay, and so I agree with the people that were saying that it would be decreasing. Now, like I said, this is a really hard one, and it's pretty much, you know, it's hard to get much more difficult here with these conceptual style ones. There's a lot going on here. Questions from anybody? Now, the other thing, too, is with a question like this, okay, I think what happens is our ability to do the math of the circuits usually is better than our conceptual way of thinking through it. Okay, so what I advise people to do is to, especially when you're starting out, try to use both of those. Okay, I mean, if you're really desperate on a problem like this, you can actually make up numbers and go through and calculate. Now, that can be slower than kind of thinking through it. But especially when you're starting out, I think that can be super helpful. And eventually your sort of math knowledge and your more conceptual knowledge will come together, and then you'll be really, you know, dangerous because you can solve just about any one of these problems. So last chance for a question on this. We'll come back to questions like this at some point. So we will return to this. But this is, like I said, about as tricky of a conceptual one as you can get. Okay, so let's go now to ones that are a little bit nicer. So here's another conceptual style one. Again, this is an old test quiz question. Which resistor has the greatest current going through it? Assume that all the resistors are equal. Okay, so discuss this with your neighbors and see what you think. Okay, so let's give ourselves maybe 10 more seconds on this one to consider this. So make sure you put your answers in. Again, if you're not sure, just put your best guess in. We don't zap you for not being right on these, for sure. So I'm going to call time here. And let's look at the, so it looks like we got the battle between B and D. Anyone want to be brave and tell me what they were thinking for either B or D or something different, if they were thinking something different? Yeah.
So resistor 1 and resistor 2 with line parallel has like more resistance R3, R4, and R5 combined. So R1, R2 will have lower strength than R3, R4, R5. And then R3 and R4 there's more resistance to that path and R3, R5 so more current going to go through R5.
So R5 has more current. Okay. Anybody else have something that they were thinking on this? So today we're sort of, these first two, we're looking at ways to use these Kirchhoff's rules to help us conceptually. So that first one, we used the loop law. Okay, it was really important that the voltage in that loop had to add up to 0. So if I went up 12 volts, I had to come down 12 volts. In this one, it's important, I think, along with what he said, that the currents at a junction have to, add up. And so the way I would think about this one is you have some current, okay? I don't even care sort of what you call it. So some current, we'll just call it I coming here. Now, when it comes here, it has to split up, and you have to account for everything. So what's going to happen is if you look at this, it's going to be I divided by 2 that way, and I divided by 2 that way, okay? It says in the problem that all resistors are equal, and so when the current comes to these 2 resistors, all right, it's going to go split up exactly in half. And as a side, I made a video sort of talking about resistors and parallel and short circuits. So I put it up on Piazza that I think would be helpful with this kind of stuff. So you guys can check that out. Just goes a little bit more in depth. But when it comes to these 2 equal paths, the current says, okay, I'm going to go equal both ones. So it's I divided by 2. All right, so we got that. So we know that those are equal. So if the question asks something about that, you're good to go with that. Then they come together, and this is going to be I again right here. And now it splits off. Okay, it's going to split off into 2 pieces again. So I'll call it, like I above and I below. Now, we can actually calculate what these are going to be, but which one is going to be bigger, I above or I below? I below, right? Because if you're an electron, right, that's sort of the easier path. Okay, and it's not like a short circuit. It's not like all of the electrons will go that way, okay, but more of them will go that way. Now, we don't have to know, okay, exactly what it is, but we know that it's going to be bigger there than the top one. And since it's bigger than the top one, that means that this current, okay, whatever it is going to be bigger than a half. okay? It's going to be bigger than a half, and so that makes, and it'll actually come out to be 2/3. But again, we don't need to know that for this one. But R5 will have the biggest current. And again, it's because we know that these currents split up, and they have to split up from the same current, right? Whenever there's a junction, the currents have to be accounted for. They can't just, that I, where it comes into the first two, and that I coming into the second one has to be the same. Questions on this, anybody? All right, and so now, leading up to the one that we had on the PCQs, so I just wanted to reiterate this. We sort of did this really quickly at the end last time. Apologies for that. But when we talk about brightness, okay, we're going to be talking about power. And so in general, we'll be asking questions about the brightness of a light bulb, which is really the brightness of a resistor, which is really asking about the power dissipated by the resistor, okay? And the power dissipated by the resistor, we know that power is the change in energy divided by time. Our energy, in a case like this, is Q times delta V. And so if you look at this, the thing that's changing is the Q, or the current. And so sort of the fundamental thing here for power is I times V, okay? And so that's, you can totally use that. But in general, I think it's easier to use one of these two here. So once you have I times V, you can take your Ohm's law and get two other variations of that. Okay, so once I have that IV, then I can say, okay, well, I know that V equals IR, and I can use that to make those two other versions. And what's nice about this is almost all the time, okay, I guess maybe occasionally we might do this, but we'll ask you to compare brightness of things that have the same resistance, two identical light bulbs. And so when you have this case and this case, if they're identical light bulbs, you know the R is the same, so you can kind of mentally just forget about that in that equation and say, okay, basically if I can tell which one has a bigger current, I know that's brighter, or if I can tell which one has a bigger voltage drop, I know that one's brighter. Okay, so then it becomes a game of trying to figure out if you can determine that or not, all right? And so someone last night said, what metric is the best to determine brightness of a bulb? I swear I've heard voltage, current, and so all three of these are true. I think these two are the useful ones, and it really depends on the circumstance. So we're going to do an example next, and we'll talk about it. I also put it up a video of doing another example of doing this, so you might want to check that out too. But it really depends, and everyone does this a little bit different. Some people love to think about the current. Some people love to think about the voltage. I really feel like if you use both of them, because sometimes, usually one is like way easier than the other, okay? And so let's just try an example now. So here's sort of a classic style problem like this. So here's 3 light bulbs. I want to rank the light bulbs in terms of brightness. So let's talk with your neighbors and see what you think about this. Okay, so I think most people have voted. And the good news is I think we did really good on this one. So we'll just go ahead and maybe give 5 more seconds. So again, put your answer in if you haven't yet. And we'll discuss. So anybody want to tell me what they were thinking before we show the answer? Anybody? Yeah, did you have... Oh.
So Kirchhoff law says current in, current out, right? So A should have higher current than B or C, and then because B and C are equal, the current splits in half, right? So B and C should be equal, and A will be greater than B.
So I think that's probably the fastest way to think about it is, in this case, in terms of current, right? So the current coming into A, you could call I. Again, you don't care what it is, but you know it's going to split up equally into B and C, which means B and C get less current. Current is one way to determine this. So A is bigger. Since B and C are identical, they're going to have the same. So A is equal to B, or A is greater. Excuse me here. That right there. Anybody have a different way they thought about it? Again, there's different ways to think about it, and we don't care how you think about it, just as long as you find a way to think about it. But I think that's probably the fastest. And so now that leads us into the one from last night. So the one from last night was like this. And so basically, that one from last night has, that same setup. In fact, the light bulbs are even labeled the same. Okay? So we know from this picture, and you guys totally just were all over this, that we can say something like A is greater than B, which is equal to C. And so now I want you to talk with your neighbors just quickly. Where do you think D and E fit into that? And try to rationalize why you think that. Okay, so go ahead and take a few minutes and do that. Okay, so I'm hearing some really great conversations, but so let's break this down. So again, we just rationalized how to do A, B, and C. So now we look at D and E. So the first thing I'm going to say is that D and E are equal. Can someone tell me why I know that? They're in series. And so what does that mean? That means that the current going into one has to be the same as the current going into the other one. Okay? You can also think about it in terms of voltage. If you do an outside loop there, right, you know that whatever the battery's voltage is, there's some increase of the battery's voltage. As you come over here, you got to go down D and down E to get back to the zero. And since they're identical, they have to have the same voltage drop. So different ways to think about it. So now they have to be equal. So then how do we figure out where they rank in the spectrum of these other ones? Okay, and that's where it gets a little bit tricky. And that's where you got to think, or at least you don't got to. There's lots of ways to do this. So first of all, I'm just going to call each one of these light bulbs to have resistance R, just to make my picture a little bit nicer. And so I'm going to break these and sort of treat them as resistors. So here's a resistor R. Okay, and here's the equivalent resistance of these two guys. If you do two resistors in parallel and find the equivalent resistance, you get R divided by 2. And then over here, I've got sort of the same picture. I've got an R here and an R over there. Okay? There's something, and then what you can do is you can break that down even a little bit further, like so, and make a picture like this. Okay, so now these guys are in series. So series, this would be 3/2 R, and over here, this one over here would be 2R. All right? So right now, what you can do is when you do that, you can then start thinking about the current that's going through those two legs, right? And so the equivalent resistance of each of those, one's 3/2, one is 2. And so what you can do is determine the current. And the current, as usual, is just going to be I equals V divided by R. Okay? And so what I can do then is say to myself, well, if we just call the voltage here to be V, for instance, okay, then the current that comes through here is going to be V divided by 3/2 R, which will work out to be V over R times 2/3. Okay, so that's the current that's going through this A here. And again, I just figured that out by using Ohm's law. The current over here is going to be V divided by 2R, and so the current over here at D would end up being I divided by, V divided by 2R, like that there. Okay, and again, I figured that out just by doing Ohm's law. Okay, so like the current that's going through A has to be, because it's the same voltage drop because they're in parallel with that battery, divided by my total resistance. So 3/2 R, so this is 2/3 V over R, and then the I over that D would be V over 2R, which is just V over 2R. And so right there, again, going by current, this is a bigger current than that one there. So I know A is the biggest. So I got that. A is the biggest. And now, just the last part before we sort of finish this up, is I know that this is going to split up in half. And so if it's 2/3 V over R, then it's going to be 1/3 V over R, splitting up into half. 1/3 is less than 1/2, and so I can finally make the deduction that A is greater than D, so D will be bigger, equal to E, which is greater than B equal to C. So that's my final determination. Again, there's lots of ways to do this. This is why it's really good to talk with a friend, because your friend might think about it a different way. But you definitely got to be careful that you're not only thinking about currents or only thinking about voltages, because either one can be super helpful in different cases. And like I said, especially when you're starting out, pull in that math, because I think people can catch up with the math a little bit faster than the conceptual side a lot of times, and so that can be really helpful, I think, when you're learning this for the first time. Okay, so here's a question from somebody. Why does a battery output more volts whenever there are two light bulbs that are parallel? So again, we're always going to assume, unless I say otherwise, that our battery, is ideal. And when you have an ideal battery with some resistors, basically there's a battery, and then the battery sees some equivalent resistance. If that resistance changes, all right, goes up or down, the current will change, all right? So that's essentially the answer. It's just that, this battery is this thing that's got this voltage difference, and the electrons want to get to that other side, and the resistance is getting in their way. If you change the resistance, either more or less can go through in a certain amount of time. And so anytime you change that R, you're going to be able to adjust the current. So a question there. And so we've been kind of dancing around these ideas today, but just to formalize this, the two Kirchhoff's rules that can be super handy. The first one is the junction rule, which just says the total currents in equals the total currents out. Okay, so we use that today. And then this idea of Kirchhoff's loop law, which really Kirchhoff's loop law is just this idea similar to we made a lot of distinctions when we talked about electric potential to be like height. It's the same sort of idea, okay? You can make this analogy. Think about you're hiking in some sort of mountainous region, and you're at some base camp, and you decide to go out and go for a hike, okay? And you might go up, and you might go down, and whatever you might do, but when you come back to your base camp, the total amount you went up has to be the same as the total amount you went down, okay? So your ups and your downs have to cancel. It's the same idea here. Okay, with any loop, and this is any loop, okay? I know when you're starting out, you're kind of like you feel guilty, but any loop will do this. If I start at one point, and if I go up or down, whatever it might be, when I get back to that same point, my total voltage drops have to add to zero. And this can be the craziest loop you can think of, as long as it's any path should work this way. All right, so it's just like that same analogy, coming through some mountainous region or something like that. So we'll do some examples to show how this works, but that's the basic rule there. And so is the Kirchhoff's voltage law work for every single loop? Yes. It works for every single loop in a circuit, okay? And so a lot of questions about this. We'll keep talking about it, but it works for, and so that's what's so great about it. Basically, my philosophy is, for me, it's easier to think about these kind of things sometimes with series and parallel. If I'm stuck, okay, the Kirchhoff's rules are where you got to go to look at more complex situations, which we'll look at in a little bit here. Okay, but for me, if I'm trying to find numbers, it's usually faster to think about it in terms of series and parallel. So I'm someone that tries to get a lot of life lessons out of TV and movies, and so here's some life lessons I've gotten out of TV and movies. So Forrest Gump, has everyone seen Forrest Gump, right? So the lesson from here is, even if you have shortcomings, as we all do, life can be a wonderful adventure. It's kind of very uplifting, right? Then you got something like this. Right, and so what's right? That's that's basically all I can get from that one, right? Let's see, the Lord of the Rings trilogy is a lot of so that's an example that it is possible to make great movies based on a book. You just got to take your time and make 3 movies, right? So it can be really great. Then there's the Hobbit trilogy, right? And so to me, that's kind of the opposite, right? Okay, there they probably went a little bit too far, right? You don't have to make every Hobbit movie into 3. Like, there's literally a scene in the first one where Gandalf is washing dishes for 20 minutes, right? So it's a little bit much. Now again, I think I told you this is my favorite TV show, probably of all time. So it's something that I've really, tried to think, what are they trying to tell us here, right? What deep life lesson? And I think I finally figured it out. Again, I'm not sure, but I think that's sort of my take on it, right? Okay, and finally, Jurassic Park. So I'm kind of dating myself. Who's seen the original Jurassic Park? Is it kind of like most of us, or am I just an old guy? Okay, so this is another one. I love this movie. I've thought a lot about the message they're trying to tell us, and this is what I really get out of it. So if you open a multi-billion-dollar real-life dinosaur park, don't only have one person in charge of all the IT. Okay, that's sort of the lesson, especially if that one person is Newman from Seinfeld, right? You're just going to set yourself up for trouble. All right, so now we're going to show you the steps to use Kirchhoff's rules. Now, I'm just going to say these are my steps. People do it differently. You don't have to do it this way. Again, on the test, I don't care how you do it as long as you get the right answer. But these are my steps. We're going to go through and kind of show you how to do this. So the first step, which is the key step, okay, like 9 times out of 10, if someone comes to me and says, I can't get this problem, this is where the mistake was made. So label your currents, and then we'll label the positive and negative for all the elements, and we'll explain how this works as we go through. With the EMF, which is the battery, it's easy. The big end of the battery is positive, the negative, or the smaller end is negative. With resistors, it's harder because with the method, it depends on which way the current is going through the resistor. And this is dependent on how you label the currents. And so this is the kind of thing that, like, if you're doing it with your buddy or your friend, you might have different answers, okay? And so you got to be careful about that. So then you choose a loop and a direction. Again, any loop in any direction, okay? But the number one question last night was, do we have to go a certain way? You can do any, it's really great. It's like total freedom. You can do any loop you want, any direction. It'll always work as long as you are careful with your signs, okay? Write down the voltage drops across the resistors. For your loop rule, use the first sign you get to. So that's sort of the way that I do it, which I think makes it easier. Again, you don't have to do it that way. If you have a way that you do it that's better for you, that's great. So list those voltages. Finally, I write down the current equation. Okay, so we're going to use the voltage drop loop rule and the junction rule to make our equations. And then finally, at that point, it's just algebra. So it's just a math problem. So once you get to there's no more physics. It's just math, okay? So here, if there is a resistor between 2 batteries, how do you tell which end of the resistor is the positive end and which one is the negative end? So we're going to go through and show this, but basically, in this model, it's the way you pick the current, Okay, so the way you pick the current determines how the voltage drops through the resistor. And the thing is, you could be wrong. Okay, unless you're a computer, it is really hard to look at these pictures and know which way the currents go. In fact, I've been doing this for years. I don't even try. I just guess currents and then go through and do the work. And then at the end, what will happen is if you guessed wrong, okay, for like say, if you guessed wrong for current I1, it'll just be, you'll get a negative answer. And that's just the math saying, hey, you guessed wrong. Okay, but again, it's super hard to know. I mean, if these were easier, you wouldn't have to be doing Kirchhoff's rules on them. So you can sit there and try to guess if you want, that's fine. But for me, I don't even bother. Okay, I just sort of jump right in. And so here's a real basic one, just to kind of give us an idea of how this setup works. Okay, just to kind of give us a flow for this idea. And I think it seemed like we did pretty good. So in this case here, okay, in this case I actually know which way the current goes. Okay, so it's a little bit of a cheat. So I'm going to say that the current is going to go this way. So I'm going to have my current I going this way. Now, when my current I goes that way, what happens is when it comes to a resistor, when the current goes to a resistor, right, it's going to be going down, okay? The voltage drops as it goes through a resistor. Your electric potential drops. And so that's what these positives and negatives are trying to represent. It's trying to say that, okay, so here's the high end of the resistor, here's the low end. It has nothing to do with the actual battery. Okay, it has to do with the way we picked the current to go. Okay, and so here, this battery, the idea is like so the current comes here. Okay, the battery lifts it up 12 volts. It goes over here, it drops, it'll end up being by 10 volts. And over here, it drops by 2 volts, and it's back down to 0 again. And so that's all that these signs mean, is they're sort of representing that this is the sort of higher end, and that's the lower end there. Okay? And so you go about and do that, and then, so this would be sort of the first step. The first step is, picking my current, writing those positive and negative signs, and then I do my loop. Okay? And just to be funny, let's start my loop over here. Okay? So I'll start my loop there, and I'll go counterclockwise, just to kind of throw everything off. Okay, so I'll go this way. So I go this way. I use the first sign that I come to. And so here it's a negative. Okay, so it's a negative, and what you write is you write the voltage drop. And so for the voltage drop for a resistor, that's just using our old friend Ohm's law. So the voltage drop for a resistor is I times R. So over here, I times R, I don't know the I, so I'll put I, and then my R is 1 ohm. Okay, so now I keep going around in my loop, and what do? I come to this one, and my first sign I come to is a negative sign again. So it's negative I times R. Again, the current is I, and this is 5 ohms. All right? And so down over here, then I write negative I times 5 ohms. And then I come down, and the first sign I come to in the battery is positive 12 volts. I keep going, I get to my starting point, and when I get there, I put equals to 0. So now this is an easy example. We're just trying to show you how the principle works. All right, you probably wouldn't do Kirchhoff's rules with this one, but it's just kind of nice to go through and do that. So then at this point, I have enough information to solve this. Okay, so here I'll say negative I times 6 ohms plus 12 volts equals 0. And then what I can do is just solve that. And so for I'll get 12 volts divided by 6 ohms, or the answer of 2 amps. Okay, so that's generally what you would be looking for. One of these problems is to find the current. And then now, right, you can go over here and then just sort of show yourself that it sort of does everything we want it to do. So over here, current of 2 times 10, so this is, current of 2 amps times 5 ohms is a voltage drop of 10. And over here, current of 2 amps times 1 ohm is a voltage drop of 2. And so again, if we do our Kirchhoff loop law, and I start here, I start from negative and get to positive, so I go up 12 volts. I come over here, start at positive, go to negative, so I go down 10 volts. Over here, I start at 0, go down 2 volts, and I'm back down where I started from. So I went up 12 and went down 12 over here. Questions on that, anybody? Yeah.
So
Yeah, so the current was 2. Again, you can go any way you want. So what would happen, what would change in this equation if I'd gone clockwise? The signs, right? And the thing is, since it equals 0, that doesn't matter. The signs don't really matter. So if I'd gone the other way, I just would have gotten positive I times 1, positive I times 5, and then negative 12. But it's the same equation. So it literally doesn't matter, and you could have started it anywhere on the loop, okay? I mean, I usually start over here or here, but you could start here, you could start anywhere you want to start, as long as wherever you start, you come back to that same point. Okay, so it's super flexible, and you don't have to follow the current. Like once you draw the current determines these positives and negatives here. And now you could have on this one, because I knew the current was going, I could have gone this way, and then this would have been positive, that would have been negative. The same thing would have happened, and just that here in your equation, these would have been positive, and here I would have gotten negative 2 amps, which is just saying, hey, you guessed your direction of current wrong. It should go the other way. Okay? And so this is a very mathematical thing, and it's very flexible. Any way you choose to do it will work. There's no sort of loop, way you have to go around the loop or anything like that. Other questions? Okay, and so here's one that's a little bit nastier. This is the kind of one that you probably would have on a quiz. So, and it would say something like, solve for the currents in all parts of the circuit. Okay, so the very first step, like I said, which is the part that I think people make the mistake on the most, is where the currents go. And so here, basically, whenever there's a junction, your currents have to break up and change. Okay, and so I think that's the number one thing I see, is that people will not have their currents change when something like that happens. And so when I did this one, I chose this here current to be I1. I1 current starts right here, goes through here, and ends over here. All right? My I2 current I had as going from here to here, and my I3 current over here is going this way here. And again, now I think in this one it turns out that my directions were right, but it doesn't matter. You could have gone the opposite way. And in fact, like in this case here, it's kind of counterintuitive that I1 is going this way, right? So what's happening is if the current is going this way, it's actually charging this battery instead of discharging it, okay? And so that's an example. I mean, this would be sort of a circuit where you're actually charging your battery or something like that, okay? But I could have guessed the other way because it's really hard to know, okay? Now, I mean, if you think about this a little bit, you can sometimes get some sort of idea, like basically what I sort of reasoned is this is a 10-volt battery that wants to go this way. This is 5 volts, so I kind of reasoned maybe you would win in that sort of battle of currents. You got like sort of 2 batteries fighting. But again, it doesn't matter as long as you're consistent. And you have to have 3 currents here, okay? You have to have 1 down here, 1 here, 1 here. Whenever there's a junction, the currents have to change, okay? Any continuous piece of wire has to have the same current. Here's the first piece of wire, the second piece of wire, the third piece of wire, okay? Questions? Anybody? So then the next step is to put in your positive and negative signs, okay? Okay, so that's sort of stuff I just said. And here's our loop laws. This is really important. So I'm saying that I1 comes in equals I2 plus I3 leaving. Okay, so that's what I said. Again, if you did this differently, you'd get a different equation for this one right here. Okay, but that's okay. It just means we'll get a negative answer in the end. And so here's the last step before you start making equations, and that's putting in these positive and negatives. So for the battery, it's just always the way it is. The big end is always positive, the little end is always negative. For the resistor, it's the way the current goes through it. When current goes through a resistor, it's a voltage drop. So it's going to come in at the high end, the positive end, and come out at the negative end, the lower end. Okay, and this is the kind of thing that if you had picked this current the other way, you would have gotten a different answer. Okay, so it's important that you're consistent. So picking the currents and then writing these little positives and negatives is important. And so here, how could two batteries offer current in different directions? Well, again, what would end up happening is one of them would end up, in general, possibly charging the other one. Okay, so that's what happens, and that's what really, most of these trickier cases will involve more than one battery. That's a question you don't really know which way the current is going to end up going in the end. Okay, and so we can just sort of go through some questions here. I think I tried to address most of those. When deciding on the loop and direction, does the loop you decide have to be in the same direction as the current? What do you think about that? No, it can be any direction you want, okay? Is it okay to keep the negative currents? You have to. If you get I as a negative, you got to keep it that way for the rest of your algebra. That's another sort of common mistake. So when talking about the charge of a resistor, is polarization the thing that is happening? What's actually making the positive? So it's not positive and negative charge. It's like a higher or lower end of your resistor. Why are we allowed to pick which end is positive and negative in the resistors? Again, because we don't know which way the current is going, and so there's some ambiguity there. Okay, so we'll pick this up next time and finish this example. I'll be down here if you have questions. See you guys.